Good morning students. Welcome to session 6 on the Riemann integration. So in this session we are going to study about the properties of Riemann integration. So that is the continuation of the previous theorems. So in the last session we studied up to 7 theorems. So in this session let us start with theorem 8. So if f is a function from a comma b to r is a bounded function, then m into b minus a, small m into b minus a is less than or equals to lower Riemann integral a to b f of x dx, which is less than or equals to upper Riemann integral f of x dx, which is less than or equals to capital M into b minus a, where small m and capital M are infimum and supremum of the function f on a comma b. Let us take the proof. We have m into b minus a, which is less, we know this one here. This is one of the previous property we studied. So m into small m into b minus a is less than or equals to lower Riemann sum LPF, which is less than or equals to upper Riemann sum UPF, which is less than or equals to capital M into b minus a. Take this one as equation number 1. For every p belongs to p of a comma b. Since we know here, since LPF is less than or equal to supremum of LPF, where p belongs to p of a comma b, and this implies here LPF is less than or equals to, we know supremum of LPF is nothing but here, this is lower Riemann integral a to b f of x dx. Take this one as equation number 2. This is from the definition we have seen here. And also since UPF is always greater than or equals to infimum of UPF, for all p belongs to a comma b. So that we know here, that is every element is greater than the lower bound here. So therefore UPF is always greater than or equals to, this is the definition again here, this is the definition of upper Riemann integral a to b f of x dx. And so or we can take here, we can take like this also, that is upper Riemann integral a to b f of x dx is less than or equals to, we can write like this also, UPF. Take this one as equation number 3. So now further we have here, we know lower Riemann integral is always less than or equals to upper Riemann integral. So I'll take this one as equation number 4. Now from equations 1, 2, 3 and 4 we have here, from observing these equations 1, 2, 3 and 4. So we have in equation 1 what we have here, in equation 1 we have here m into b minus a is less than or equals to LPF. So LPF is nothing but here LPF is less than or equals to a to b f of x dx. And in equation 3 we can see here, this is a to b f of x dx is less than or equals to UPF. So from all these equations we can say here m into b minus a is less than or equals to LPF, which is less than or equals to lower Riemann integral, and which is less than or equals to upper Riemann integral, and it is less than or equals to UPF, and which is less than or equals to capital M into b minus a. So this implies here, this is m into b minus a is less than or equals to lower Riemann integral from f of x dx, and it is less than or equals to upper Riemann integral of f of x dx, it is less than or equals to capital M into b minus a. So this is all about the proof of this theorem. Now let us take next theorem. So if f is a if f belongs to R of a comma b, then small m into b minus a is less than or equals to integration from a to b f of x dx, which is less than or equals to capital M into b minus a. So where small m and capital M are infimum and supremum of the function f on a comma b. Since here f belongs to R of a comma b, then this implies, we know this lower Riemann integral is equals to upper Riemann integral, and it is equals to the Riemann integral a to b f of x dx. This we studied. Take this one as equation number 1. So now we know that here this m into b minus a is always less than or equals to lower Riemann integral a to b f of x dx by previous theorem, it is. So and this implies here m into b minus a is less than or equals to, this lower Riemann integral is again same as integration from a to b f of x dx. So take this one as equation number 2. So this is from equation number 1 we can say here. And also since upper Riemann integral is always less than or equals to capital M into b minus a, this is again from theorem 8th, previous theorem only we have seen here, this is less than upper Riemann integral is always less than or equals to m into b minus a. So again we know this upper Riemann integral is again same as only Riemann integral a to b f of x dx, which is less than or equals to m into b minus a. This we can take from equation number 1. So now combining all these equations, combining equations 2 and 3 here. So in equation 2 what we have here, m into b minus a, which is less than or equals to a to b f of x dx, and it is less than or equals to m into b minus a. So this implies here, so m into b minus a is less than or equals to a to b f of x dx, and it is less than or equals to m into b minus a. So this is the proof of this theorem. Let us take one more theorem. We can also call it as a Darboux theorem. So that is here, the statement of this theorem is, if f is a function from a comma b to R is bounded function, then for each epsilon greater than 0 there exists a delta greater than 0 such that, first one, UPF is less than upper Riemann integral f of x dx plus epsilon, and LPF is greater than or equals to lower Riemann integral f of x dx minus epsilon. For each p belongs to p of a comma b with norm of p is less than or equals to delta. Take proof. Since f is bounded on this interval a comma b, then there exists a real number k greater than 0 such that mod of f of x is less than k for all x belongs to a comma b. So that is here, this is f is bounded in this interval, no? There exists some real number k such that its modulus is always less than k here. Let us take the first proof. We know that upper Riemann integral f of x dx is equals to infimum of UPF. So this is by the definition. So by the definition of greatest lower bound, we have for each epsilon greater than 0. So infimum of UPF plus epsilon by 2 is not a lower bound, because here it is the lower bound, no? So therefore plus epsilon by 2 is not a lower bound. That is, there exists p1 belongs to p of a comma b such that what here, UPF is less than infimum of UPF plus epsilon by 2. So which implies here UPF is less than, integration from here, this is what here, this is infimum of UPF is nothing but here upper Riemann integral, that is a to b f of x dx plus this epsilon by 2. Take this one as equation number 1. Let us take the partition P1. So that is here a comma b, no? We divided this interval as x0, x1, x2, etc. up to xp, it is equals to b, has p minus 1 points excluding endpoints here, excluding a and b here, because here x0 to p means it is p plus 1 points and p plus 1 points here. So then by second, take one more second point. That is, by definition, lower Riemann integral is equal to supremum of LPF. Take this one as equation number 4. Then by the definition of least upper bound we have for each epsilon greater than 0. So even supremum of LPF minus epsilon by 2 cannot be the upper bound. So therefore, a partition P1 belongs to P of a comma b such that LP1F is greater than supremum of LPF minus epsilon by 2. So this implies here LP1F is greater than, this is, we know the definition of this one, supremum of LPF is lower Riemann bound, lower Riemann integral a to b f of x dx, and this minus epsilon by 2. Take this one as equation number 5. So let P1 is equals to, again you divide this interval as p minus 1 points excluding the endpoints here. So now we have to choose here delta such that epsilon by 2 is equals to 2k into p minus 1 into delta. Take this one as equation number 6 as we have done in previous case. Suppose P is any partition with norm P greater than less than delta, then P may contain some or none of the partition points of this belonging to P1. So that is here, if P union P1 is equals to P is a refinement of P, then it contains at most P minus 1 additional points. It is exactly like previous case. So LPF plus 2k into P minus 1 delta is greater than LP2F, which is greater than LP1F. So again it is to take this point in this side, it becomes here, this is nothing but here lower Riemann integral, and take it is equals to, this is again, so it is equals to here LPF is greater than, take this point in this side, it becomes minus 2k P minus 1 for delta, and we know here it is 2k P minus 1 delta we have taken here as epsilon by 2. So it is LPF is greater than integration from a to b f of x dx minus epsilon by 2 minus epsilon by 2 is what here? It is equals to epsilon. So that is LPF is greater than lower Riemann integral f of x dx minus epsilon for all p with norm p greater than norm p less than delta. So this is all about the proof of this theorem. So if you find any difficulties, first you go through this, first you write the notes, then go through this theorem once. After that, if you find any difficulties, feel free to ask me any doubt by calling or in WhatsApp also you can ask me the question. So here this is the partition P1, we have divided, it has P minus 1 points, no? So excluding endpoints. So now you have to choose here epsilon greater than 0 such that epsilon by 2 is equals to, you have to choose this value such that epsilon by 2 is equals to 2k into P minus 1 into delta, and take this one as equation number 2. So now suppose that here, suppose P is any partition with norm P is less than delta. Then P may be contain some or none of the partition points here XR are equals to 1 to P minus 1 belonging to P1 here, but it may contains or may not contains. So if P union P1 is equals to P2, then P2 is the refinement of P and contains at most P minus 1 additional points. So here P union P1 means here P union P means it contains, it is the combination of both, it is the sum of all the values of P and P1. So it contains at most P minus 1 additional points other than the P2 here. So that is UPF minus 2k into P minus 1 into delta is less than or equals to UPF. It is less than or equals to UPF because here minus some value, no, it is definitely less than or equals to UPF, or it is less than or equals to UP1F because here P1 is contained in here what we have here. So here P1 is contained in P, no, so therefore we can take here it is less than UP1F. So UPF minus 2k into P minus 1 delta, which is less than, so it is lower Riemann integral a to b. We know here UPF is less than this upper Riemann integral f of x dx plus epsilon by 2 from equation number 1 we can say here. This is from equation number 1 we have seen here. So it is less than, it is equals to this one here. So this implies here UPF is less than, you take this value minus 2k into P minus 1 in this side, it becomes plus 2k P minus 1 into delta. So UPF is less than upper Riemann integral f of x dx plus epsilon by 2 plus epsilon by 2 because here 2k into P minus 1 into delta we have seen here, it is, we have taken this one as here epsilon by 2. So this is also plus epsilon by 2. After adding these two we will get here epsilon. So UPF is less than upper Riemann integral plus epsilon we can take here.